We'll get started. So today the topic for discussion is linear state observers. So this would be the counterpart for controller design, which is what we were talking about in the previous lecture. So this lecture we are going to talk about observers. There's a difference between controller and observer, very fundamental difference. In controller, um, there is this notion of actuator saturation, whereas in observer, there is no saturation at all because all the observers are being designed on computer systems. So as long as you have 64-bit or 128-bit representation for real numbers, there isn't any saturation. I mean, for most real systems, there isn't any saturation that's going to happen. And consequently, you will be able to design observers with whatever gains you like. The only problem with observers is that, well, that's a problem with controllers as well. So sometimes when you apply a signal to a controller, the controller may have some variation. Uh, Generally speaking, those variations comes from either component degradation or whatever. I mean, there are like same component, like same motor might work differently depending on the temperature, depending on some variations in the environment, depending on some degradation within that motor over time. So in some sense, the actuators give you the, like, once you give it the input signal, the actuator is going to give you the appropriate output. There will be some noise associated with it. In observer, there could be noise associated with sensing as well. And so if you use very high gain observers, which we are going to talk about today, you might see that those noises can get amplified. So definitely there is some amount of restraint you want to have in the context of observers as well. And those are the kind of topics that we will be talking about today. So let's remind you of the linear system that is under consideration here. So this is my linear system. I want to recall some notions from the observability theory that we talked about a couple of weeks back. So I just want to do a recap. So define. So we have, well, we have yt is given by c e raised to at x naught plus integral 0 to t c e raised to a t minus tau vu tau so define y tilde t equals to yt minus this whole thing, and that becomes equal to c e raised to at x naught and the definition and the results that we talked about in the observability lecture. I think this was lecture 16, but I could be wrong, lecture 15 or 16. So this was something we studied, I think mid-March or early March. X is unobservable. Okay. Before we jump onto that, x naught is observable if and only if we can determine x naught from yt ut t greater than equal to 0 by a time capital T greater than 0. So if I'm given a, well, maybe and then x naught is unobservable. This was the first definition. The second fact I want you to remind you from that lecture, x naught is unobservable if and only if y tilde t equals to 0 for all t. So y tilde t is right here. And the third thing that I want to remind you from that lecture is x naught unobservable if and only if x naught is null of observability matrix if and only if x naught is in the null space of observability Gramian. These are the three results I want you to remember from that lecture. Oh, there is a fourth result also. Sorry. Let me write the fourth one. Rank observability equals to n implies that x naught is w observable 0t inverse integral 0 to t Okay, so I've reminded you everything that I wanted to remind you from lecture. Let me get that lecture. lecture 16. This is all the recap from lecture 16. We studied this 3 weeks ago, so I assume some of you may not recall it. So I just wanted to write down all the stuff we talked about in that lecture. So this notion of, what I want to point out here is that the notion of observability was defined for a very specific reason. The reason was, why did we want something to be observable? The reason was, if you give me the observations, if you give me the measurement and the actions from time 0 to time capital T for some t greater than 0, I am, and assuming that the system is observable, which means that the rank of the observability matrix is n, I can actually do this integral. I can compute y tilde. So I'm given yt and ut. I know the system matrices A, B, and C. So I can compute this part. I can subtract it from yt. I can construct y tilde t. And then I can substitute this y tilde tau here, integrate from 0 to t, invert the observability Gramian, and I can reconstruct x naught if the system is observable. If the system is unobservable, then in that case, there are some values of x naught such that this y tilde of t, is always going to be equal to 0 for all t greater than equal to 0, right? And this happens only if x naught is in the null space of the observability matrix, which happens only if x naught is in the null space of the observability Gramian. Okay. So the notion of observability was defined for figuring out what x naught is. I don't care about x 0.5, I don't care about x 1.5, and so on and so forth. All I care about is x naught. You have a question?
Yes. So are we talking about, or are we assuming like the whole system to be unobservable, or are we talking about some specific, like could some specific states be unobservable and other states be observable in this scenario?
That's right. So some states, in the case of unobservable system, there is a non-trivial unobservable subspace, right? Which means that so this equation will always be true for x naught equals to 0. So if you start from rest, x naught equals to 0, this y tilde t will always be 0, because this is 0. So whatever matrix you multiply it to, it will always be 0. On the other hand, if you start from a non-trivial x naught, non-zero x naught, you have two possibilities. One possibility is it will be equal to 0. One possibility is it's not equal to 0. If it is equal to 0, then x naught is unobservable, which means if y tilde t equals to 0, then this is always 0. So you cannot really differentiate between different values of x naught, and so that forms an unobservable subspace, and we talked about it in lecture 16. So that's the unobservable subspace is essentially the null space of the observability matrix. If your x naught is not in the null space of the observability matrix, so it's orthogonal to it, then you can you can figure it out. You can identify, and those equations were given in lecture 15 and 16. So 15 was about controllability, 16 was about observability. But as we will talk about today, there is some notion of duality between these two topics. So something that you can do for reachable systems, you can also do for observable or unobservable systems. So anyways, we'll talk about it in a bit. But this whole notion was defined purely because I want to figure out what my initial state was, even though I didn't know, even though I only have the measurement and I have the action. Okay. My goal today is slightly different. My goal today is, I have this linear system. I'm given the linear system. compute x hat t, which is approximately equal to xt. So I want to estimate the state for all t. This would be my ideal goal. This is what I would want to do in an ideal world. So I don't have the complete state measurement. So I'm sitting in this room. I don't have the temperature. So I'm measuring the temperature of this room. I'm measuring what's happening at all the air handling units. So I have the UT for all the air handling units in the building. But I only have one measurement, which is the temperature of this room. And I want to figure out what the temperature of every room within this building is going to be. Okay, so my xt is the temperature of every room in the building. So there may be like 50 or 60 different rooms in the building. But I only have one measurement, which is the temperature of this room. I have all the actions, UT, from the entire energy system, or rather the air conditioning system of this entire building. So I might have like 10 air handling units, 10 heat exchangers or whatever. So I have all that information embedded here. I have the temperature of one room. I want to figure out what the temperature of all the other rooms in the building is going to be. And ideally, I want my estimate to be as close to xt as possible. That's my ultimate goal. So the question is, how would you do that? So let's go back to 1950s. You are building a rocket for NASA. That rocket is supposed to go to the moon. The rocket has maybe like a bunch of sensors that are taking the measurement. And you have a very good model of the rocket. So you have all this A, B, C, D matrices. You went to the physics department, you went to the aerospace department, and somebody there gave you the exact model for the system. And the problem is that you want to measure the state. You can't measure the state. All you have is a bunch of measurements from your sensors. You know exactly how much fuel was burnt at the rocket. You know exactly what the ailerons and different control surfaces on the rockets are doing. And you want to figure out what the state of the system is. So what would you do? What would your approach be? Just come up with some wild approach, whatever comes to your mind. You know the system, you have the measurement, you have the control actions. You want to estimate the state. How would you estimate? How do you design your estimator? I want to write something like x hat dot t equals to something something. But I don't know x naught. If I knew x naught, then the entire problem is very easy, right? If I know ut, I know x naught, I can figure out what the equation is going to look like. But the problem is I don't know x naught. I only have observations and I only have actions. And I want to figure out the entire trajectory. Remember, the goal for observability was only to figure out x naught. I don't care about what happens at x 0.5. Now I care about what happens at x 0.5. I care about what happens at x1. I care about what happens at x2. And actually, I want to estimate all of those values for the entire duration from time t0 to t equals to infinity. What would you do? Yes, please.
If you're claiming to know the A, B, C, and D matrices,
Yeah.
could you just take YT minus DUT and then multiply it by the inverse of C? Like, could we not just solve the observation equation to get x0 and then work forward from there?
That's a good thought. Can you explain a little bit in somewhat mathematical terms? So C is not invertible, right?
So we're assuming the amount.
Yeah, I mean you can have a very high dimensional state. So for instance, in this room example, I have 50 dimensional state, but I have one dimensional observation, which is the temperature of this room. So C is not invertible. But yeah, if C was invertible, then it's easy. So that's called fully observed system, where you're observing all the states. So then you can invert the C matrix and you can get xt directly from there. Yeah, okay. So one idea, okay, fine. So if C was invertible, you can look at yt, you can subtract dut from there, multiply it by C inverse, and you get the value of xt. So definitely that's one idea, but in our case, C is not invertible. Yes, please.
We start with random guess for XT, and then since you know the ABC, we can just run through it and get the X dot comparison for YT and minimize the error between
Okay.
model estimates and what the Ashman says.
Okay, so I will. Okay, so if I understand this correctly, so I'm going to guess a random X naught. I'm going to run this system for time t. Then what am I going to do?
So I would get the best estimate for all the states, the X dot t, and then I could compare. Sorry, YT.
So I'm doing the comparison, and then what happens?
So we could run the YT from the CET model,
Uh-huh.
and you would get the estimated YT. And then
Right, that's what this particular thing is giving you, this expression. So I initialize the X naught randomly, then I do this computation, I get some Y hat t or something,
compare it with the original YT session.
compare it with original YT, and then what happens?
Try to reduce the error.
How do you reduce the error?
Change the X naught
Okay, okay,
Presumably it becomes, you could either do gradient descent by taking the derivative and trying to find the way that would reduce your error from YT the most, or you could
Wonderful. Okay.
optimization problem.
Okay, so I guess you guys are banking towards the optimization formulation. Certainly, optimization formulation is a valid formulation, but that's not the formulation we'll be studying today. Okay, but that's definitely a valid formulation, which is to assume some value of x naught, do this computation of y hat t, and then try to minimize the L2 norm between yt and y hat t, and try to recompute the value of x naught. That's going to give you the best estimate for the entire trajectory. Once you figure that value of x naught out, then you can do the simulation for the rest of the time, and you can get the value of x hat t. So definitely using optimization is one way to do it. Any other thoughts that comes to your mind? Something which is, so remember, you are going to, this is 1950s, you're going to moon. Optimization is a very new field. Actually, optimization was defined like 10 years ago in World War II because people wanted to optimize the movement of troops and supplies during the World War II. And we don't quite have the computational power to be able to do the optimization. I don't know what sort of machines they used to do the calculations. I think it was shown in that movie Enigma. What is that called? Like, you used to use punch cards to do the computation, like additions and subtractions and stuff. So you can't really run complicated optimization algorithms there. So it has to be something which is simpler than optimization. Optimization definitely works. It's what you would use in 2026, but it's not something you would use in 1950s. Any other thoughts that comes to your mind? Okay. So here is what we will do. I'm going to define this x hat t, x hat dot t to be equal to a hat x hat t plus but plus k times yt minus y hat t, and my y hat t is going to be equal to c x hat t plus dot. So this k is called the observer gain. So there were elements in our discussion that we concluded just now. So the element was, I'll start with some initial guess. I will compute y hat t. I know exactly what yt is because that's given, that information is given to me. I'll look at the difference The only thing was that earlier you wanted to minimize the L2 distance between this. And now what I'm doing is multiplying this error by a gain matrix K called the observer gain. And I'm adding it to the differential equation for x hat t. So if the gain is if this error is 0, if this error is 0, then x hat t evolves according to the same expression as the original system. But if this one is non-zero, it gets multiplied by the observer gain, and then you compute the value of x hat t. So this is the linear observer. This is a linear observer. You can of course do more complicated operations here. It's not clear what the value of those complicated operations are going to be, but definitely you can do this linear operation and you can get the value of x hat t. So I can write my x hat dot t to be a minus kc x hat t b minus kd b minus kd k. Okay, so I substitute this y hat t expression here, and I get this this way of writing the evolution equation for x hat t. I'm going to initialize it with some nominal value of x hat 0. It doesn't have to be accurate, it just has to be a good estimate. I don't care if that estimate is like accurate, but I have a feeling, gut feeling, so this comes from the gut feeling of the designer. Okay, I'm going to define the error process xt minus x hat t. Can someone tell me what E dot of t looks like? So I have x dot of t, which I can write from here, and I have x hat of t, sorry, x hat dot of t, which I get from here. So what is E dot of t? The error process, the differential equation for the error. So let's look at that. It's a xt plus but minus a minus kc x hat t plus b minus kdb k and okay, yt is cxt plus dut. It looks pretty horrible. There's a lot of terms here, but can someone simplify this for me and tell me what E dot T looks like?
ECE x at t plus negative kb negative the u. Oh yeah, this was that on
Yeah, it's cxt plus dut. Cxt plus, because I have yt here, so yt is cxt plus dut. So this one is substituted in terms of x and u. This ut remains ut. I have b minus kd and I have k here. And I have this whole bunch of expressions before that.
Yeah, so it's just, you take the second expression, you drop out the a and you drop out the b.
So what do we get in the end?
kc x at t plus negative kd.
Okay, so what we are going to get is a minus kc et. So this kd, this minus kd ut and this k dut, they are going to cancel each other. You will have but here, you have but here, that's going to get cancelled with each other. And you have a xt and you have kc xt. So that, should there be a negative sign?
Yes, you can see negative sign from k.
Oh, I see. Here?
Yeah.
Yeah, there should be a negative sign. Thank you. Right. This is a positive sign here, so it will become negative here. Okay, wonderful. So now everything worked out. Okay, so I have a minus kc times x minus x hat, and I can replace x minus x hat with the error et. Okay, so after doing all this computation, I get that error evolves, the error process evolves according to this fashion. So what is E of t? It's exponential a minus kct E0. Okay, what was our goal? Our goal was, I know how to solve. This is just a linear system thing, right? So E dot t evolves according to some matrix times E of t. I take the matrix exponential multiplied by the initial error. I get the error at time t. What do I want the error to be? I want error to be close to 0, right? We want error to be close to 0. Eventually, I know that the error will not be 0 in the beginning, but as I collect more data, my error should go to 0. Why would the error go to 0? Why should this error go to 0? What's my, that was my original goal. What is my goal prime? What is the updated goal? This k is a free parameter, right? I can pick whatever k I want because that's the observer gain, right? So the goal prime is compute k such that what? Why should this error go to 0? Under what conditions will the error go to 0? Sorry?
KC must be equal to
Not really. This kc, no, I don't think that's the case. When would this matrix exponential go to 0? So my initial error could be large. It's non-zero. My initial error, because I have the original x naught and I have my initial guess. So my E naught is non-zero. When would this matrix exponential go to 0?
All the values are less than 1, or less than 0.
Less than 0. So real part of eigenvalue of A minus Kc should be less than 0 for all I. So all eigenvalues of A minus Kc should have negative real part. In that case, the error process is going to go to 0 exponentially fast, which will help us achieve our goal of having the estimate close to the original xt. Does this look familiar? Does this look something that we have seen before? Have we seen this before? When did we see this? Not in stability. So in stability, so this part comes from stability. So system is stable, this linear system is stable if the real part of the eigenvalue of the matrix is less than 0. So that comes from stability. But remember, when we were talking about controller design, what was my goal? Find f such that real part of lambda I of a plus bf is less than 0. Do you remember this? This was the controller design goal. So this was last lecture. So I think today's is lecture 20th. So this was lecture 19. So it should be fresh on your mind. Oh, not 19 actually, lecture 18, sorry. We took 2 lectures on controller design. So this was in lecture 18. So I want to find a gain matrix F, the controller gain matrix F. This was under the assumption that I can observe the entire state. So I can just multiply f by xt, and I wanted the eigenvalues to be negative. The real part of the eigenvalue should be negative. That was for the first goal, which was stability. So I want to use the controller to make the system stable. And then later on, we changed the idea a little bit, and we said that, okay, I want to find f so that the eigenvalue is placed at a specific location. And then we made it even more complicated and said, I want to find a value of f so that eigenvalue has a specific form, and then the eigenvector also has a specific form. So we studied 3 different ways or 4 different ways of controller design. The 4th one was using optimization and Riccati equation. So this problem looks somewhat similar to this, but you know there is a small difference. This f is post multiplied by b, but k is pre multiplied by c. That's the only difference, and that's an important difference. So this k is pre multiplied by c. So this is what I'm choosing. Here I'm choosing f, but this f is actually post multiplied by b. Okay. You know, we have talked about so many different algorithms for computing the value of f so that this particular thing is satisfied. I don't want to rewrite my code. I want to use the same code that I've written in lecture 18 and 19. How do I solve this problem? Okay, there were a bunch of theorems we studied about controller design. So under what conditions can you design a controller? Under what conditions can you do pole placement? So if you have non-trivial, unreachable subspace, then you cannot quite do the controller design to place all the poles. So unreachable poles cannot be changed. The reachable poles can be changed, and so we figured out some way of doing that. I want to, like, I have written all that code. I have like a huge Python package that does that. Now I want to use the same Python package for this particular problem, but I'm facing a hurdle, which is this post multiplication, pre multiplication thing. How can I make something that is pre multiplied post multiplied?
Similarity transform on C.
Similarity transform will not change the order of multiplication of matrices. Anyone has any thoughts?
So matrix multiplied by its transpose is identity.
Not quite. Okay, so here is a cool thing, cool fact. A B transpose equals to B transpose A transpose. So if I take the transpose of the matrix, what is pre-multiplied become post-multiplied, but with a transpose. Okay. So remember this idea, and let's try to build upon this idea. Okay, so the question now is, knowing this fact, and knowing the fact that you have this Python package to do this or MATLAB package to do this, how would you solve this problem? So think about it while I erase the board. Sorry, I'm using A and B here, but this A and B differs from the A and B that we use for the system matrices. So I can solve this. How do I solve this? You know, another cool fact, if you transpose the matrix, the eigenvalues don't change. Eigenvectors change, but eigenvalues don't change. Okay, so A and A transpose have the same eigenvalues. So what I'm going to do is I'll come up with my goal double prime, compute K such that the real part of lambda I of A transpose minus C transpose K transpose is less than 0. And now whatever code I have written for this, I can give the code A transpose and minus C transpose and get F, and then take the F transpose, set K equals to F transpose. So to my code, I'm going to pass A transpose and minus C transpose. These are the two matrices, right? I get the value of F. So F should be the same as K transpose. So I'm going to set K equals to F transpose. And that's how I will be able to use the same Python package that I wrote for controller design. I can use the same package to do the observer design as well. I can find out the K matrix. Always remember that the eigenvalues of this matrix and eigenvalues of this matrix are the same. Eigenvectors of this matrix and eigenvectors of this matrix are not the same. They are different. But eigenvalues are the same. Generally speaking, the goal for controller design is always to make sure that the error goes to 0. We don't quite care about the eigenvector placement. right? So that's the case. We cared about it in the context of controller design, but we don't quite care about it in the context of observer design. But you can do it. You can still do it if you wanted to. It's just going to be a bit harder, and it's not something that anybody is interested in, so it's not there in books and other references. Okay. What else do you remember from controller design? So under what conditions can we design controllers that achieves this objective? So when the system is controllable, turns out you need system to be observable to be able to design a K that meets this particular criteria. You can do the pole placement of A minus KC by picking an appropriate matrix K if and only if the system is observable. So let's talk about it now. So any questions so far? I want to pause here for questions. I think we covered a lot of stuff so far. And now I want to get into the theorems and proofs about this particular problem statement. Okay, the idea is clear. We have a very specific way of computing x hat using this linear gain matrix multiplied by the error in observations. That led us to computing the error in the state estimate, which is given by this particular expression. When will this error go to 0? If I can make sure that the real part of the eigenvalues is strictly negative. How do I get the real part of the eigenvalue strictly negative? Well, I can apply the same idea from controller design with slightly transformed matrices in order to get the appropriate K matrix for this. Now we want to understand the fundamental limitations. Under what conditions can we actually design observers that are able to achieve the objective that we want the observer to achieve, which is the error should be stable. Okay, so let's do, let me remind you from a month back. Lemma 9.18. Of the book, which says ECE observable if and only if there exists a K such that lambda I of A minus KC equals to lambda I bar. So I can do the pole placement. So I want to write here in layman terms pole placement for error process is possible if and only if system is observable. That's plain English. So in plain English, you can do the pole placement for error process if and only if the system is observable. Remember, at the beginning of the lecture, I mentioned that the goal for observability, or at least the definition for observability, was defined if I'm given the observations and actions, I can compute x naught. That's it. That was the only goal for observability. I can compute x naught. I can figure out what the initial state is if you give me the observations and actions. Now you see that this notion of observability is expanding. Okay, so system is observable, then you can do a lot more with that particular system. In particular, you can do the pole placement in that particular situation, and you can make sure that the error process goes to zero exponentially fast. Can someone tell me how quickly would the error process go to zero? Like what controls the error going to zero? It's the magnitude of this real part of the eigenvalue. So if you plot these eigenvalues here on the complex plane, so this is the complex plane, this is imaginary axis, this is the real axis, and I'm plotting all of these eigenvalues of this. This is lambda 1, a minus kc, this is lambda 2, a minus kc, this is lambda 3, a minus kc. How quickly the error goes to zero depends on how far this particular point is from the origin. So you look at the rightmost eigenvalue, the real part of the rightmost eigenvalue, and if it is close to the origin, the error will go to zero very slowly. If it is far away from the origin, the error will go to zero very fast. Okay, so this one in this case controls the how quickly the error process is going to zero. Okay, wonderful. So assume that the system is observable. I can actually pick all of these lambda 1 to lambda 5. I can pick it. I have the freedom to pick it. So how about this? How about I pick all of these eigenvalue to be here. All my 5 eigenvalue, well, one has to be on the real axis. They all have to have complex conjugate pairs because this is a real system. So I pick these eigenvalues. Why is this undesirable? I can pick, right? So the point was that I can pick these eigenvalues anywhere in the complex plane, and I should be able to do the pole placement for the observable system. Why wouldn't I want something like this? So everything is far away from the origin, so the error is going to decay to zero extremely fast. Within a matter of a few seconds, my error will be negligible. It will be zero, close to zero. You know what the reason is? The problem with this particular design is that your k will be very, very large. When your k is very, very large, then what happens? Remember, this x hat of t is a x hat t plus b ut plus k yt minus y hat t. So if k is very large and I have errors in the observations, errors in the measurement, this error could be just a sensor noise. So if you look at the temperature sensor in this room, it might be saying that it is 70 Fahrenheit, but if you look at the raw sensor reading, which is probably sensing every second or every 10 seconds or every 1 minute, the temperature reading, the sensor reading will not be 70 Fahrenheit. It will be 70.001, 70.25, 69.89, and so on and so forth. So this is at 0 second, this is at 10 second, this is at 20 second. Even though the temperature is not varying so wildly from one time step to another. So this is like there is inherent sensor noise in every sensor that you buy in the market. Some sensors, of course, the more expensive the sensor is, the more accurate it's going to be, the less variation and less noise you are going to see in that sensor. But most sensors will have this sort of variation and noise, as a result of which, if you pick a very high value of k, your x hat t, sorry, this should be x hat dot, your x hat dot t will vary very widely because of this noise process that drives the measurement values. So that's why you don't want your k to be very large, and that's why you don't want to place your poles far away from the origin. You ideally want your poles to be close to the origin. I mean, well, not close to the origin. You want to pick the value of k appropriately, or the poles appropriately, so that the value of k is not very high, so that you don't amplify the sensor noise in your estimate. Okay, so that's roughly what the theory for placing the pole is. Remember that there is no actuator saturation here. All of this is happening in your computer's memory, as a result of which it doesn't really matter what value of k you pick. As long as you can fit it within the memory, it's completely fine. You can pick the value of k. But you ideally want to have a trade-off between noise rejection in your estimator versus the speed at which the error converges to zero. And so you have to balance the two different objectives appropriately, and that's from one application to another, from one sensor to another, you will have completely different considerations. So I'll just leave it up to you, so that in the future you can pick appropriate values of lambdas and you can do the pole placement for observable systems. Any questions on this before I jump to the next point? Okay. Wonderful. Now let's assume you have unobservable system. Let's see what happens in the unobservable system. So I can do a similarity transform of unobservable system. I can come up with a hat equals to q inverse aq. This was taught earlier in the March, so this is lemma 6.4, page 242. I'm going to talk about the standard form for the unobservable system. We had talked about it, I think, in early first week of March. So I'm just reminding it from my memory. CQ. So the matrix Q is constructed. You can look at the construction of matrix Q in the book on page 242. And the A hat is actually given by A11, A12, A220, and C hat is given by C10. This is the observer standard form. I think, what is page 242, right? Standard form. Okay, so this is the standard form for unobservable system. So I can do the similarity transform and I can get the standard form for the unobservable system. I can do the same thing like we did for the controller design. So I'll look at the standard form, I'll design the observer gain for the standard form, and then I'll pull that particular observer gain into the original system. So let's try to do that. Let's do k hat. Pick k hat to be k1 and k2. So this is the this has the same dimension as a11, and this one would have the same, sorry, the same, not the dimension, this would be in the number of rows here is the same as the number of rows in a11. Number of rows here is the same as the number of rows in a22. Okay. So what is a hat minus k hat c hat? Can someone do this expression? Can someone tell me what this matrix looks like? So this is a11, 0, a21. Sorry, this should be a21 and a22. Okay, so now the question is, my question is that if I have an unobserved, so for observable system, I can do the pole placement, my life is good. Somebody will tell me what the noise process for the measurement device looks like, and I can define appropriate values of the eigenvalues, lambda bar I, so that I can apply the Python package that I had created with appropriate matrices. I can figure out what value of k should be. Now I'm giving you an unobservable system. Okay, now things have changed. So I cannot quite do the pole placement for unobservable system, but the error process, or at least some sort of similarity transform of the error process, will follow the eigenvalues of the unobservable system. What do you notice here about the error process? So E hat of t, how quickly will it go to 0? Well, it depends on the eigenvalues of this matrix and the eigenvalues of this matrix. Values of this particular matrix I can control because I have this parameter k1 here that I can control. Eigenvalues of this matrix, well, should this be k2? I think this should be k2. Yeah, this should be k2. Can you make that correction? So I can control the eigenvalues of this matrix. I cannot control the eigenvalues of this matrix. So if I want the error to go to 0, what should happen? So ET will go to 0 I can do the pole placement here. So I can make sure that the eigenvalues have negative real part. I cannot do anything about it. So I want lambda I of a22 to have negative real part. So all eigenvalues of a22 must have negative real part. Only then my error would go to 0. Okay. So my error will go to 0 only if all eigenvalues of the unobservable subspace are have negative real part. So it's automatically stable. So if you're not able to see the unobservable subspace, that's fine, because eventually the xt there is going to go to 0 anyway. So I don't care. The only thing I care about is for the observable part, I can pick the value of k1 so that the eigenvalues of this is strictly negative by applying the same principles as Leva 9.18. So this one I can control, this one I cannot control. This one I can make sure that the eigenvalues have negative real part. This one I cannot, so I have to make an assumption that if this one is stable, then I will have an observer that will be stable and the error process will go to 0. Any questions so far? So that's the theory. That's in principle the theory for observer design. You have a system. You first have to figure out whether it's observable or unobservable. If it is observable, no problem. You can apply the pole placement algorithm from previous lectures to figure out the pole for A minus Kc. So you're not quite figuring out the pole for A minus Kc. What you're doing is looking at A transpose and minus C transpose, and you're doing the pole placement using the previous code that you had written. If the system is unobservable, you transform the system into its standard form. You isolate the unobservable subspace and the observable subspace separately. You can do the pole placement for the observable part. For the unobservable part, you assume that the eigenvalues have negative real part, so you are in good shape, and then you can do the you can drive the error process to 0 using appropriate values of the gain matrix K. You will also notice that K2 actually doesn't quite play a significant role in placing the eigenvalues of this matrix. So you may choose to keep it, you may choose to ignore it, but that's up to you. But K1 definitely changes the eigenvalue of this matrix. K2 would change the eigenstructure, like the eigenvectors of this matrix, but not the eigenvalues. Okay. So what have we learned so far? If I'm able to observe the states perfectly, I can design a controller, I can use a feedback controller to stabilize the system, to place the poles, and to place the eigenvectors. If the system is observable, I can construct a linear observer by picking an appropriate matrix K, and then I can drive the error process to 0, so I can reconstruct the state of the system fairly easily, and the estimate will converge to the true state in a reasonable amount of time. Now we want to merge the two things. We want to do we have a system, we have a complicated system. We want to do the observer design and we want to do the controller design, both of them at the same time. Okay, so this is the topic for the next class. I'm not going to start that topic today, but I want to motivate that discussion today. So I have a system x dot t equals to, so next class, this is I have this linear system. I'm not observing the entire state. I'm just making some measurements. I want to design a controller U. Okay, so my goal is to pick UT using all the past information that I have generated in that particular system so that the feedback system is stable. Let's go back to 1960s. So it's 1950, I have to send a rocket to the space. I have to put a man on the moon. Those are the two important missions from 1950s. There is this new theory of linear systems, and I have this linear dynamical model for my rocket that's supposed to go into the space. I have to control that rocket at every point of time. I'm making a bunch of observations about the rocket. I know exactly what all things I've done in the past. I have to use this information progressively to compute UT, which will be then fed back, and hopefully the feedback system would be stable, which means that the rocket will go along the intended trajectory into the space. Think about it. Going to the moon is like it's the same thing as shooting a bullet and hoping that it will hit the target, right? So it's a very big space, right? The earth is moving, the moon is moving, like everything is moving, the earth is rotating, the moon is rotating. You want to send something from earth to a very specific point in the moon. You definitely want, remember that the goal there, the xt, is the actual trajectory of the rocket minus the intended trajectory of the rocket. Okay, so that's what the notion of xt there is. The state is not the position of the rocket, but the current position of the rocket minus the expected position of the rocket according to our calculation. That's the error, that's the xt that we are trying to minimize. We want the system to be stable, which means that we want xt to be close to 0. If xt is close to 0, then the rocket is going on the intended trajectory. The rocket is not deviating from the intended trajectory. So that's why I want the system to be stable. So I want to create a feedback law that makes the system stable. Now, if this problem was posed to you, what would you do? You know about observer design, you know about controller design, but the assumptions for the observer design is completely different from the assumptions for the controller design. In particular, in the controller design, you expect the uncontrollable part of the system to be stable, and you are making full measurement of the state. Okay, you don't have partial measurement of the state. Here you are making partial measurement of the state. In the observer design, you're saying that, look, I don't have any information about the state, so I come up with this error process. I pick appropriate gain matrix K, observer gain matrix K, so that the error process is stable, as a result of which eventually my x hat t is converging to x of t. how would you mix the two? How would you merge the two different thought processes together? So that's the topic that we will talk about in the next class, and we'll stumble upon a very important and crucial result for controller design, especially for dynamical systems of this type, which is you can actually design your observer and controller separately. So there is a notion of separation. It's called the separation principle. It was one of the very famous discoveries of 1960s and 1970s. Millions of paper, well, not millions, but hundreds of paper have been written on this notion of separation principle. And it's amazing that in linear systems, you can actually design your controller as if you are making the full state measurement. You can design your observer using the technique we discussed in today's class. You can merge the two, and the overall system is going to work as intended. It's not going to blow up. Things are going to work out just fine. That is the reason why for most of the control systems, people tend to run Kalman filter first, figure out what the state is, and use that state, the Kalman estimate, for doing the control design. Okay, that is the way people design controllers for a long time, and that seems to be the appropriate way to design the control system, as we will prove in the next class that there is this notion of separation. I think the book doesn't emphasize this notion of separation as well as I want to, because it's not true for general nonlinear systems. That wouldn't be true, but for linear system that is true. And in fact, all the nonlinear systems also have this separation built into it, purely because people have carried over that information from linear systems. But frankly speaking, for nonlinear systems, you can't have this separation. You can't have a separation of estimation and control. But people use it because it's very simple, it's easy to understand, it's easy to debug if you have made a mistake. But as far as the optimality goes and as far as the applicability goes, that is true for linear system. So I'm going to emphasize on this separation principle. We'll talk about separation principle in the next class, and we'll do the overall controller design for this class of feedback systems. The other thing that I want to make note of is next class we will be done with the syllabus for this class. Okay, so next week onwards I'm going to talk about things that are completely irrelevant to the syllabus of this class. So what I'm going to do is I'll talk about the discrete time systems, and I'm going to cover this notion of stability, observability, controllability, controller design, observer design for discrete time systems. So that way at least you will have in your arsenal both continuous time system and discrete time system stuff. I'm not going to cover all the theorems and proofs for discrete time systems, but I'll give you the information so that it will be handy, and whenever you need it you can use it for both continuous time as well as for discrete time systems. But discrete time systems is not part of the syllabus, so if you want to attend the class, you're welcome to. If you don't want to attend the class, that's fine too. But I'll try to cover the discrete time systems. So we'll have 4 lectures. We have 4 lectures. Next week 2 lectures, and the week after that 2 lectures. So those 4 lectures will be devoted to discrete time. Thank you so much, and I'll see you on Thursday.